Okay, so I kind of got cut off on that last video, but we're going to be talking about this restoring force. So as the spring is compressed, the force is going to want to go back towards equilibrium. So the spring force is that way. And then over here, as the spring is stretched out, it's going to want to go back. And so we have our spring force towards here. And that's why we call it a restoring force. So Hooke's law is going to be the relationship between the amount that it's been displaced and the force exerted on it. And so if you can kind of picture, if I smush this even more, it's going to have more of a force pushing it back towards equilibrium. Just as if I pull the spring further away from equilibrium, it's going to have a stronger force. So the force is directly proportional to the distance that it's been pulled away from its equilibrium. And that's what Hooke's law says. The force exerted by a spring is equal to the spring constant K, and we're going to talk about what K equals to, this here, right here, times the distance the spring is from its equilibrium. So the force is directly proportional to the displacement from equilibrium. This K value is called a spring constant, right here, spring constant, and it's inherent in the spring itself. So each spring has a different spring constant. Basically, it's how smushy or how springy the spring is. So if it's something like a slinky that has a lot of easily stretch in and out, it's going to have a lower value. If you're going to have something that's very tough that you can't push in and stretch out, then the K value is going to be higher. And the units for K are Newton meters. Okay, so let's try an example using Hooke's law. Okay, we have a mass of we have a mass of 0.5 kilograms. It's attached to a vertical spring, and it stretches the spring 2 centimeters from its original equilibrium position. What is the spring constant? So we have this mass right here. I put it, this is its equilibrium position. It stretches 2 centimeters or 0.02 meters away from the equilibrium position. So our given is 0.55 kilograms. It stretches 0.02 meters, and our unknown is K. So if I have a free body diagram of the object right here, I have the spring force that's going this way. And because it's being pulled down from equilibrium, the spring force wants to pull it back towards it's heading up, and gravitational force is going down. Well, our spring force is equal to negative K delta X, and our gravitational force is mg. So I'm going to say that the net force on this box right here is going to be the Fs, the spring force, minus the mg. And we know that it's going to be equal to 0 because it's not moving. So we're going to have our spring force will be equal to our gravitational force. So we have negative K delta X is equal to mg. Well, we know all this information, so we can solve for K is equal mg delta X, and it's negative delta X. Well, K equals m, which we know is 0.55 kilograms. G is just our old-fashioned gravity, 9.8 meters per second squared. And then the negative delta X, well, delta X is a negative, so it's negative 0.02 meters. And if we calculate this, we end up with 270 Newton meters. And this is our value of K. K is always a positive number. Okay, so let's take this another step. Okay, so now we're able to find out our spring constant and our spring force. Now we're going to be talking about spring potential energy. So if I pull something away, and here's a bow and arrow, if I'm going to pull it this way and hold it right here, I'm going to be able to feel the pull of that spring that wants to pull me back in towards equilibrium. I can feel it in my muscles. Well, this has, at this point right here, it has potential energy based on the spring. And if I let it go, this arrow is going to turn into a lot of kinetic energy. So the potential energy here will be equal to the kinetic energy of the arrow downrange. Now let's bring it back into our spring mass system here. If this is our equilibrium and I pull the block away from the equilibrium position, the delta X value, it's going to have potential energy. And then over here, it's back in its equilibrium position. So here, the potential energy, which we say PE, but it's an S, it's no longer gravitational. Remember that PE gravitational was NGH, and we learned this when we talked about energy. Now, our potential energy based on the spring is equal to 1/2 K, that's our spring constant, delta X squared. That delta X is the amount that it's been displaced from equilibrium position. And if you can see here, it's squared, so that negative value won't show up. And so potential energy is always going to be a positive value. Okay, so now we know that the energy, we talked about this before when we did that energy roller coaster thing in class, and I said that this was the potential energy based on the spring. Well, now you see where we're going to be dealing with that. Okay. So now we're going to talk about simple pendulums, and they basically are the same as a spring. They might look a little bit different, but a simple pendulum is just going to be a string with a mass on here. The string we're going to eliminate and assume that it's massless, so it's not really going to play anything into the equation. But if I pull a mass out of its equilibrium position, right here is our x equals 0, our equilibrium position, and I'm going to pull it out of the way with a theta. Now this theta has to be very, very small. So for when theta is very small, we're going to have periodic motion or simple harmonic motion. If we pull this thing out where it's a large theta, then we're going to have some other factors are going to come into play. And tomorrow during class, I'll show you some examples. As long as theta is small, and when we talk about small, we're talking about less than 15 degrees. So we have a very small theta here. We end up with simple harmonic motion. Okay, so right here, we have this is going to be our potential energy. And remember, a spring is going to have an arc curvature right here, and this is going to be our equilibrium position. So if I were to draw a free body diagram like we did of the spring in the last example, we have now tension. We don't have a spring that's pulling it back into equilibrium, and then we have gravitational force. So what we're going to have here is, what is the force that brings this pendulum back to its equilibrium position? Well, the restoring force is this right here. This is our restoring force for a pendulum, is the gravitational restoring force, is our Fg or mg. Gravity is what pulls this pendulum back into its equilibrium position. Okay, so for a spring, we have the spring force is the restoring force, and for a pendulum, gravitational force brings it back into equilibrium. Okay, so let's look at some samples that show the common ground between the spring and the pendulum. So what we're going to do here is we're going to look at these two situations first, and then we're going to look at these two situations. Well, right here, the pendulum is pulled away from equilibrium position, and so is the spring. So I've pulled the spring away from equilibrium, I've pulled the pendulum away from equilibrium. At this point, we have a maximum displacement, okay? If this is going to be our delta x, it's a maximum displacement, and over here, we've pulled it out a theta over here, and this is our maximum displacement as well. Well, when we have maximum displacement, we have the maximum potential energy. So our maximum potential energy is here, and our maximum spring potential energy is when we've pulled the spring out of its equilibrium position. At this point, we said that the force is the restoring force, and it's based on the amount that it's been pulled from its equilibrium. So because we're at maximum displacement, we also have our maximum force. In this case, our force is going to be pulling it this way. Our restoring force, in this case, it's going to be this way. We also, because it's maximum force, and we know that force is mass times acceleration, we also have our maximum acceleration when we're at the maximum displacement. And we have minimum velocity. So if you can kind of picture a swing going back and forth, when it hits its maximum displacement, the swing actually stops moving for a small time. and that would be the velocity up here. Minimum velocity, meaning it's zero, there is no velocity. Therefore, the kinetic energy is also minimum or zero. So we're going to be talking about maximum potential energy to minimal or zero kinetic energy when we're at its maximum displacement. Now let's look at the same two situations when they're at equilibrium. So now the pendulum swings back down into equilibrium. The spring now springs back into equilibrium. So we have a minimum displacement or a zero displacement. Therefore, our potential energy is also minimal or zero. So at equilibrium, the potential energy is zero. Because the potential energy is zero, the minimal force. We have a zero force at equilibrium. That means we have a zero acceleration at equilibrium as well. And we are now reversed where we have our maximum velocity. And because we have our maximum velocity at equilibrium, we have our maximum kinetic energy. So if you can kind of picture, we're going to be maximum potential energy, zero kinetic energy, and as that pendulum swings back towards equilibrium, this is what's going to be happening. And then it's just going to go back and forth. And the same thing with the spring. It's going to be maximum potential energy, maximum kinetic, and then on the other side it's going to have maximum potential, maximum kinetic, maximum potential, back and forth and back and forth. Okay, and that is our last slide for today. And don't forget to do the assignment on Edline tonight, and we'll see you tomorrow in class.